Because logarithms are related to exponents, they are exponents, they have properties that are similar to those of exponent expressions, exponential expressions. So for example, if I have the log of some product, so we have x times y as the input into a logarithm, we can then separate that product into two separate logarithms that are being added together. And this is reminiscent of if I have two like bases, 2 to the b to the second times b to the third, we know that we can combine those exponents by adding them. So the idea is if we're multiplying like bases, we can add the exponents to end up with a single base with a single exponent. And so here, if I have a product, if I'm multiplying inside of a logarithm, I can separate it out into the addition of two separate logarithms. And then similarly, log of quotients. If I'm taking the log of two things that are being divided, so x over y in this case, I can separate it into the difference of those two logarithms, with whatever's in the numerator going first, and then whatever's in the denominator is going to be subtracted. And so this is, again, reminiscent of if we're dividing with like bases. So if I have b to the fifth over b to the third, we know that we can subtract those exponents, and so we've got b to the second in this circumstance. So when we're dividing inside of a logarithm, we're going to subtract those separate logarithms when we separate it out, just like over here, when we're dividing with like bases, we can subtract those exponents. And then the last example that we have here is something called the log of powers. And so what this means is that when we're taking the log of something that has an exponent in it, so in this case it's y to the p power, we can take that exponent and bring it to the front as a coefficient in front of that logarithm. And so we've got p times the log of just y. And so if we think to our exponent rules, if I have b squared to the third power, if I have an exponent being raised to another exponent, we're going to multiply those exponents to get the new exponent. So in this case, if I have a logarithm, something inside of a logarithm being raised to some exponent, I can bring that to the front, and then I'm going to end up multiplying. So these properties are all connected to our exponent properties because, again, logarithms are exponents. And so in the examples that we have here, we want to try to apply these logarithm rules to rewrite these as series of logarithms that are being added and subtracted instead of in this combined format. So there's a couple properties we can apply on this first one. So I'm first going to see it as a to the fourth times b to the fifth inside of that logarithm. And so I'm going to use that log of products to separate those two pieces into separate logarithms. So I'm going to have log of a to the fourth plus log of b to the fifth. And so I've separated it because it's that a to the fourth times b to the fifth. The product inside the logarithm means I can rewrite it with addition as two separate logarithms. And then I also have this exponent that's on the inside of each of these logarithms. A to the fourth, so using that log of powers, I can bring that to the front as a coefficient. And then the log of b to the fifth, I can bring that exponent to the front. So I can finish this off by rewriting it with those exponents out front as coefficients. And so we end up with 4 times the log of just a plus 5 times the log of just b. So we've applied two of those properties, log of products to separate it into two separate logarithms, and then log of powers to bring those exponents to the front as coefficients. So in this next example, we can see we're taking the log of two variables that are being divided. So we're going to use our log of quotients rule to separate this into two separate logarithms that are being subtracted, with whatever is in the numerator being positive and whatever's in the denominator being negative. So we'll start off with log of y cubed minus the log of z squared. So similar to what we did on the previous question, we're going to separate it into two separate logarithms, but we're going to subtract, or whatever's in the denominator ends up negative. And so now we're going to use that log of powers rule to bring these two exponents, the 3 and the 2, as coefficients out front. And so our final result here in the fully expanded form is going to be 3 times the log of y, and then minus 2 times the log of z. For the last one, we have 3 pieces inside the logarithm. We have x times the square root of y in the top, so both of those pieces will be positive when we start to expand this expression, but then we're dividing by e on the bottom, so that will be subtracted as a logarithm. And our log this time is the natural log instead of the base 10 log that we had in these previous couple of examples. But that doesn't change anything, it just means we're going to use natural logs throughout instead of that base 10 log, that common log. So we're going to have natural log of x, the first piece that's in the numerator, plus the natural log of the square root of y, the second piece that's in the numerator, and then we're going to subtract the natural log of e that we have in the denominator. Now, there's a couple things we can still do to simplify this expression. This natural log of x, there's nothing that we can do there, but for the second part here, we've got plus the natural log of root y, which if we rewrite it in exponent form would be y to the 1/2 power. Remember that the square root of y is the same thing as writing it as a 1/2 exponent. So that means I'm going to be able to bring that exponent to the front and write out in front of that part of the expression. So the natural log of x piece is going to stay put. We can make this adjustment on the middle, the natural log of root y. And then for the last piece here, we've got the natural log of e. And if you'll recall, we have a property that says when the log base and the number you're taking the log of match, your answer is always 1. And if we recall that natural log is really log base e, it's just a different way that we write it. So we've got basically log base e of e here. Natural log of e, log base e of e is going to equal 1. So I can make that minus 1 instead of natural log of e. It's just a way I can simplify my expression. So our final result here, I've got natural log of x, and then plus, I've brought this 1/2 exponent to the front, so I have 1/2 times the natural log of y, and then after simplifying, we just have a minus 1 on the back end to finish it out.